Sorry. But anyway, so Vincent asked me to come, and 5 years ago, I finally said yes. But unfortunately, we have a pandemic. so I came here yesterday, and I really realized that this is a really beautiful island, a lot of good science activities. I understand why my former students and postdocs who attended this school had such a high opinions on this school. But anyway, I originally tried to talk about the topological effect in 4D, 5D transition metal oxide. But I decided to change my topic at the last minute. So there's a couple of reasons. First, my previous, the speaker, the Professor Cavalier, did such an excellent presentation, so there might be nothing too much I can give to you. So another reason is that we recently find out that a lot of interesting phenomena, emergent phenomena in strontium leucine. As you know, that I think many of you are experimentalists, so you think that strontium leucine is a very simple material, so you understand almost everything in here. But today I try to show there's a lot of the new thing actually coming in strontium leucine. So this is the basic outline of my talk. So I will give an introduction, and I will explain to you about a lot of the transport interesting properties on ultra-thin film. And if I have time, maybe I will cover some of the magnetism. And at the end, I try to discuss a bit about the topological band structures on strontium leucine, and particularly, I try to address the nodal futures. So one of the big questions in this community is that how we can discover the novel emergent phenomena in transition metal oxide, and also how we can control such a kind of phenomena in real application by using heterostructures. And also, so my talk do not have any equation, so very simple. So be relaxed, and you can ask any question, okay, if you want to have, okay? So a lot of the people in here always deal with the oxide, and oxide has a numerous structure, but one of the most important and well-known structure is the perovskite, which chemical formula is AbO3. So usually this element has a transition metal oxide ions in the middle, surrounded by the oxygen. So we call this the metal oxygen octahedra. And if you arrange this one in the three-dimensional array, you have an empty space. Then we put either strontium, calcium, lanthanum, and so on. So in this material, a lot of the conduction actually happen through this metal oxygen, the network that is actually formed in the three-dimensional way. But since the transition metal oxide can have a lot of the different fillings in d electrons, depending on this, the filling factor, we can have a lot of different property. For example, this is a few examples what can be happen. So ferroelectricity, ferroelasticity, multiferroics. The day of tomorrow, maybe I will talk about the flexoelectricity. But today, I will mainly concentrated on metal-initial transition, magnetism, and some of the topological properties and so on. So why we are looking at transition metal oxide? One of the important reasons is that there are the important interactions, physical interactions in our system. This is a periodic table of all of our elements. Now, in the transition metal oxide, it's actually on this line. So there's a 3D transition metal oxide, 4D, 5D. And in this oxide, the wave functions are a little bit localized than SOP orbit wave functions. So it can have a large correlations. So many people from the beginning talk about the effect of the on-cycler interaction and the competition between the U and T. T is the hopping integral. So that's basically the bandwidth. The competition between those two usually determine metal-initial transition. And when it becomes an insulator, we call this a mod insulator. And it has a very long history. So in the beginning, many people look at the 3D transition metal oxide. So U and T value is around few to several electron volt. However, people started looking at 4D transition metal oxide, and they begin to realize that it has a large Hund-SrRuO coupling. The typical value is about 0.5 electron volt, but the important vector is the 3J or something like that. And in those cases, it can become as large as 2 electron volt, so they can be comparable. So another kind of physics coming out that is called as Hund-SrRuO physics. And nowadays, many people start looking at even some of the metallic system, even though there has a eternal phenomena, this J will start to play an important role. That is called as a Hund's metal. And that is particularly, this concept has been developed by Paris group. And also, if you go to the 5D transition metal oxide, the spin-off coupling start to play an important role. The spin-off coupling is usually proportional to the fourth orders of the atomic number. So in here it's very large, but in 3D it's very small. But in 5D transition metal oxide, J can be as large as 0.5 or 0.7 electron. So they become comparable. So new physics will come out. And about 15 years ago, our group is the first group who proposed that in strontium iridae, the J effective 1 state will play a very important role. After that, people started looking at the importance of the spin-off coupling on 5D transition oxide, and they tried to see what kind of a role they will play. And nowadays, this topological effect become paradigm shift during last 22 decades. But the largeness of the spin-off coupling will play a very important role to understand the topological effect of oxide. But unfortunately, so far, compared to the 2D materials, the number of the topological effect that's observed in oxide is fairly small. But that's one of the reasons we have to keep looking for the effect. But anyway, so in transition metal oxide, we have a strong, the on-site polar interaction, which is characterized by U, and the exchange interaction between the electrons at the different orbital, we call this a Hund-SrRuO. And also large, if the spin-off coupling become large, we will have a spin-off coupling. That will play an important role. And a lot of people in this room are making a lot of the different kind of the heterostructure out of the transition metal oxide. So by doing that, we can control charge, spin, lattice, orbital, even dimension and spin-off coupling. So the interactions between this kind of the degree of freedom will give a lot of the new emergent phenomena. And so this is one of the way we are looking for the new emergent phenomena in this field. So in this talk, we try to introduce you our new, very interesting experimental setup, which combine the PLD with rather in situ ALPS and lead and lease and so on. So many of the people, we actually looking at the transport properties of the transition metal oxide. But that is usually good, but when we make the film thinner and thinner and thinner, then we will start to have a problem. Suppose we have a perfect system which will have a stop flow growth. So when you deposit something, it starts from growth from the edges. But when you try to approach to the one unit cell limit, even though it's a one unit cell, some places it is broken down, some places the overlays will become a 2 unit cell. So this conduction channel will break down near the step edge of the substrate in the ultra-thin limit. So if you try to do the DC transport, you may get the insulator, but you are not sure that it's an intrinsically insulator or it's all coming from the breaking down of this conduction channel near the step edges. So we need some other tool which can actually intrinsically looking at those kind of the transport property, electrical property. So one of the good way is the ALPS. So that's the reason last 15 or 20 years, we started a program to combine with a PLD with ALPS, but we all failed. It's not that easy. But recently, we got some success. That's the reason I try to show some result over here. And also, if you approach the one unit cell limit, then any kind of disorder will play a very important role. So localization effect will be huge, and so on. So just measuring the DC transport cannot guarantee that you are in the metallic or insulating region. So how do we try to do for a long time is that we try to combine PLD with the in situ ALPS. So I think many of you already know what is the ALPS means. It's a Beijing method to measure the electron structure. So I will try not explain the detail, but you can look at it. Any kind of references. So the big, actually, the enhancement came in because the Chang-Young Kim joined our program, and he's a real expert in ALPS. So he started working with me, try to building a cluster system to start the electron structures on transition metal oxide. So this is a schematic, the picture. So we have a PLD chamber over here, and this is the MBE over here. We can measure the spin ALPS and XPS. We can do the ALPS and laser ALPS over here. There's another preparation chamber. There's a schematic diagram. This is a real-looking system. So it's actually viewed 180 the other way. But there's an oxide PLD over here. And there's a MBE over here. Now we can measure the spin ALPS, and here. So if we make the film, we can transfer, and we can measure the spin ALPS, so we measure the ALPS to look at the electron structure. And this, I think, at least a lot of groups in this field try to develop this kind of system for a long time, but it was not that easy. There's quite a few regions, but I will not go to the detail. But not many people really succeeded in making this kind of film. So I think one of the only good leading group who are doing very good at it is the Cornell group. And they actually use the MBE instead of the PLD and doing the electron structure studies. But anyway, we can, for the strontium luteinate, one of the good reasons is that it has a step flow mode, so we can really grow the high quality thin film. So this is a lead pattern, and also if you look at the AFM, it has a very atomically smooth the surfaces. So this is an ideal system for ALPS because in order to measure the ALPS, you need a very, very smooth surface. And they call this ALPS of smooth, they say. ALPS of surfaces, they say. So we actually, for the strontium luteinate, it's relatively easy to reach that kind of limit. So this is the data from the Cornell, just measured about 10 years ago, and they grow the film by using oxide MBE and so on, and they have a beautiful dispersion curve and Fermi surfaces and so on. This is the film that is grown by PLD. In the beginning, many people said that PLD, you cannot make it work with ALPS. But we realized that we have a beautiful, very similar dispersion curves, and our Fermi surface looks even better. But anyway, so nowadays we can do this kind of experiment. So today I want to discuss about the strontium luteinate. So let's try to introduce you about the basic properties of strontium luteinate first. So as I mentioned before, that this is important interactions in the 3D, 4D, 5D transition metal oxide. But lutetium is actually located over here in the middle of the periodic table, where the U and T is about 3 or 4 electron volt. J is a 0.5, 1.5 is about 2 electron volt. Supermic coupling is a little small, 0.3, but still comparable. So they later on, so they will play a very important role in the topological property. But since U value and J value are very similar, so the correlations are coming from either from the Martinez as well as the Huntinez. So strontium leucine has also rhombic structure, so called as the PMNA structure, but it's not cubic, or so it has small distortions of the oxygen octahedral. They call this as OOR, so oxygen octahedral rotation. So in plane is a rotation by theta, and from the vertical view, it has a tilting angle. So depending on theta and pi, the property will be changed. We think that this is a metallic system, so small change in theta and pi will not matter that much, but really it does in this material system. In the Grace notation, so it is A minus C plus, so that means that if you look at from the C direction, this first layer and second layer, the OR is coherently rotated. But if you look at this direction, they are like this. And when we put the leucinium inside of the oxygen octahedra, then we'll have a crystal field splitting. T2G electrons has a wave function that is pointing outside of actually in a space that there is no oxygens in it. But the x squared minus y squared and g squares, the wave function is pointing to the direction of the oxygen. So it has a high energy state compared to this one, and we call this is a crystal field splitting. So now, in the strontium leucinate, we have 4 electrons, so we have to fill in up the 4 electrons in these 5 orbitals. So one of the easiest ways that we just put the 4 electrons in T2G. So that is the Lorentz energy state. And it has a metallic behavior, particularly on the 160. Here is the ferromagnetic transition occurs. It has a T-square behavior, and they believe that it has a Fermi liquid-like behavior. And so metallic all the way up. And actually, it is metallic even higher temperature and breaking the iorephal limit. And so that's the reason they originally called this is a band metallicity. So for 20 years, many people are interested in why the mean free path of electrons in here is even smaller than the atomic lattice distance. But nowadays, they think about everything in terms of the Hund's metal and so on. But anyway, it has a very good metallicity. So that's one of the reasons many people are using strontium leucinate in this room, because it's a very ideal material for the electrode. So when you make devices, you can have a strontium leucinate bottom layer. You can have a very perfect atomic smooth, as well as it is a highly metallic. So it can be an ideal material for electrode material. So that's the reason many people in this community are working on strontium leucinate. It also has the interesting magnetism around 160 Kelvin, and it becomes ferromagnetic. And so people start to think that it's maybe coming related to the Stoner mechanism and so on, and there is a debate about it. But so nowadays, many people think that it's coming from Stoner mechanism. And also, the J is a 0.5 electron volt. So Hund's coupling play an important role. So orbital degeneracy effect will play a very important role. So that's the reason from about 15 years ago, the Paris group started to propose about this Hund's metal concept in here. And also about 20 years ago, the Japanese group, Professor Nagaosa, actually proposed that it can have an anomalous Hall effect, which is actually coming from the very phase. This is a pioneering work in this oxide field, and many people start looking at the topological effect after this. That's important works over here. So that's all hidden in here. But one of the really important messages is that strontium leucinate are very, very difficult to grow as a high-quality single crystal. We try to looking at a lot of the optical property and those things by using the single crystal, strontium leucinate single crystal. About 10 years ago, at the time, there's only 3 groups which has a reasonable quality single crystal, but their quality is still less than our film. So that's the reason why we have to study strontium-lutetium in film. And another reason we are interested in strontium-lutetium 1 and 3 compound is that the layered strontium-lutetium compound, 2,1,4 compound, has the superconductivity. So this one has the layered perovskite structure, but Professor Maeno, about 30 years ago, discovered the superconductivity, which is around 1.5 Kelvin. Under the uniaxial stress, it can be as large as 3 Kelvin. So for a long time, many people believed that this is a P-wave superconductor, and they believed that originally thought that this is a really good candidate for topological superconductor. However, recently, they did all the experiment again, something like night shift, neutron scattering, and so on, and they found that they begin to realize that it's maybe not a P-wave superconductor. So there is a lot of debate still going on this compound. But experimentally, it's quite difficult to grow this thin film. Maybe later on, if you ask a question, I can answer why, okay? But anyway, so the important question is that our 1 unit cell strontium-lutetium film, or SrRuO film in the 2D limit, can have a very similar property as this one. Can we discover superconductivity? And so on. That kind of question we can raise. So far, unfortunately, we couldn't find the superconductivity yet, but maybe, who knows? So, in order to understand the electronic structure of the strontium-lutetium thin film in the 2D limit, we have to start to understand the simple, the band structure near the Fermi surface. So if you did this kind of the 2D limit calculation, you have this Fermi surface. It seems in the beginning a little difficult to see what's going on, but if you look at the structure, it's not that bad. So, for example, this one around the endpoint, if you combine, this is a circle. So in 2D, if you have an XY layer like this, unlimited, extended to the surface, you should have a circular Fermi shape. So this gamma band is actually coming from XY orbitals that is standing on the top. On the other hand, we have a XY orbital as well as a YG and GX orbital, but they are pointing this way, is terminated by the substrate and the air. So it has only one-dimensional channel. So that's the reason you have a dispersion curve like this, one-dimensional. So if you look at this one, we can understand this is coming from XY and YG. And this is all coming from XY band. It's very simple. Now, if we turn on the magnetization, I told you that it has a ferromagnetic transition around 160 Kelvin. So at a low temperature, it will go into the ferromagnetic state. Then the spin will be splitted. So there's a majority band and minority band. So this band will be splitted like this. So the red line is a majority band. Blue line is a minority band. But there is still some band crossing over here. But if you turn on the spin-orbit coupling, then the degeneracy over there will be lifted. And that is exactly the Professor Cavalier mentioned about this morning. So that's the reason the topological effect will play a very important role in the property of strontium-lutetium. In addition, if you look at this two-dimensional, the 2D strontium-lutetium, so the 2,1,4 compound, it has a huge effect on the calcium doping or substitutional doping. For example, if you dope this strontium with the calcium, this octahedral oxygen octahedra will become tilted and rotated, and this is a tilting angle, and this is a rotation angle, and so on. So there's a large tilting and rotation happen. Then this occupation number of the orbitals are changing significantly as well. So if you look at this one, so the pure calcium leucinate 214 is a really good insulator. And there many people originally believe it's a mod insulator. On the other hand, this is 2.0 is a metallic, but it has a superconductivity at the end. Then in the middle like this, it has a complicated phase diagram like this. So if you approach strontium leucinate 1 and 3 compound in the 2D limit, we maybe have the similar phase diagram, or we can at least play with the oxygen octahedral tilting and rotation, and we can find out the new emerging phenomena. That's a very simple idea we try to pursue in the group. So far it's the introduction. So are there any questions? Too simple? Easy to understand? You already know all this physics because you always deal with the strontium leucinate. But anyway, so if there's no questions, then let me move on. So now in this session, I will try to talk about the transport property, particularly related to the metal-insulator transition. So when we making a strontium leucinate thin film, one of the questions we always had in our mind is how thin strontium leucinate film we should make in order to use as an electrode. So as we decrease the film thickness and thickness and thickness, smaller and smaller and smaller, then finally maybe the metallicity will disappear. So many people have that question. So in Japanese school in 1998, so the 4 mono layer of strontium leucinate is an insulator, 6 mono layer it become metallic and so on. So they say the fundamental limit should be around here. And surprisingly, a lot of after that actually reported that the 4 units might be a limit. However, recently there's some work done by some Seongkyungan University in Korea, and they said that when you make a superlattice, they can make this metallic layer by 2 unicell and so on. However, we addressed this problem in year 2009. And so we had growth of film with the various thicknesses. If you look at it, 27 unicell is metallic. Keep decrease the film thickness. Even to the 2 unicell, we can make a metallic film. The black line is a 2 unicell, sorry. This is a 3 unicell. So 2 unicell is metallic. So how about the 1 unicell? But 1 unicell, we have a big problem at the step edges. So what we did is we did the STS, scanning spectroscopy, and one here, and we have a small number, but finite tensile state at the surface. That means that even for the 1 unicell sample, it's a metallic. And also, the kink in the DC legislative properties are related to the ferromagnetic transition. So if you look at this one, up to 3 unicell, you have a kink, but 2 unicell doesn't have a kink. So we think that the ferromagnetic critical thickness is about the 3 unicell. So we proposed this one, but a lot of the people in the community doesn't believe, and starting this way. But we think that it's probably coming from how high quality you can grow film. For example, if you grow the 4 unicell film like this, not like this, then you have insulating behavior. So the quality of the film play a very important role, particularly in this kind of the ultra thin limit. The next question is that why the ferromagnetism disappear at 3 unicell? Why it does not keep persisting until 1 unicell? In order to understand that one, we collaborate with the theory people. So usually for the experimentalist, it's usually good to have a very good theoretician groups nearby. So at SNU, Jeju News Group did the theory calculation of the DFT. And they actually provide a very simple and interesting schematic diagrams for us. So for example, For one unit cell sample, xy is a 2D character, so you have this kind of bottom singularity problem over here. But yg and gx, you have a 1D-like density of state. So if you combine, you will have this finite density of state. But if you make a 4-unit cell growth, then there's a 1, 2, 3, 4 layer. Then these density of state will be looks like this. But if you combine this one with the xy, you have this is a final total density of state. This state has a more higher density near the Fermi surface than this one. So by Stoner mechanism, it can become ferromagnetic, but this is not. This is their explanation. So they call that in here, along the y direction, or along the g direction, there is a quantum confinement effect, but it is depending on the orbital. That's the reason they call this. It's an orbital selective quantum confinement effect. So with these pictures, we can explain why ferromagnetism disappeared as 3-unit cell. But so far, it is most of them are theory and indirect experimental evidence. Do we have more explicit experimental evidences for that? So we decided, using our new cluster chambers, we decided to do the ALPS for 2-unit cell sample. So the film, when you grow the SrO and STO 001 surfaces, we got 2-unit cell, and 4-unit cell is metallic, but 3-unit cell, borderline, 2-unit cell insulator. This is IO for legal limits over here, right over here. So originally thought that, oh, maybe the critical thickness is of the transport, maybe the 2 or 3-unit cell or something like that. But we are not sure that it's coming from the step edges. So we decided to do ALPS, and to our disappointment, there's no state observed near the Fermi surface. So this is actually different from our observations over here. So what's going on? Do you have an answer? Oh, that's one of the way, good way. But we try to make a better film, so we try to away from disorder effect as much as possible. And our film is very high quality, so we think that that may be not the origin. And also, if that is the true, then it's not that very interesting. Yes? So what do you mean by surface conducting state? So in ALPS, the important thing is that there are charging effects for the insulating sample. So when you're doing the experiment, the charge will building up at the surfaces. So if that has a really highly conducting sample on the top, then all the electron will move out, so there is no charging effect. However, if there's a breaking of the channel, then the electron will building up on the top surfaces, so you cannot have photon emission anymore. So it looks like an insulating sample. So what we did is we make a small changes in configuration, like this. So, of course, SrO is grown STO, but below that, between this STO, we grow about 4 unit cell of SrO film. Then through tunneling, some of the charge that is building up over here will be transported in here and make a very nice conduction. So the charging effect will disappear. Very simple idea. Then you can see that for unit cell, you have a very beautiful Fermi surface ALPS data. Even for the 1 unit cell, you have some data. And it's do the angle average, the signal, you can see there's a finite element of the photon emission signal over there. So 1 unit cell is metallic. So I think this is the first experimental observation of the clear Fermi surface is on 1 unit cell SrO film. This is actually agree with our some of old data that is about 14 years ago. And also, we want to check about the fundamental thickness of ferromagnetism. Fortunately, we have a spin alphas. So we did. So for 1, 2 unit cell, there's no change in signal. But from 3 unit cell, you can see the splitting of the majority and minority band. So ferromagnetism should appear at the 3 unit cell, possibly coming from orbital selective quantum confinement. So questions? Too simple. This morning I tried to explain to you a very simple phenomena. So please relax, but ask any question if you have in your mind. Yes?
Like, why not just use a conducting substrate like instead of using this structure?
You mean about the superconductivity?
I mean, probing the 1 unit cell, like you could use a conducting substrate as well, right?
I think you are also working on oxide thin film. Okay, so in oxide thin film, everybody knows that it is extremely important what kind of substrate you have to use. Particularly for the very ultra thin film, that the symmetry at the surface is like to translate it to the top layer. So if you use a different kind of substrate, then we are actually working on different kind of physics. So we have to be extremely careful. And many people are using strontium titanate because that has a very good surfaces and easy to use, and the substrate preparation method is well established and so on. But for the other substrate, we do not have that kind of the opportunity. So that's the reason in here we use the strontium titanate. Yes? Yes. Yeah. Niobium doped STO is a conducting substrate. But in this kind of the ultra thin film study, the film grown on STO are quite different from those people grown on niobium doped STO. So yeah, we tried that way as well, but unfortunately we couldn't succeed. Yes, at the back. Yeah, always the film thickness is a very difficult to control. Let's see. So there's a two-way. One of the ways is by using the TEM, and you try to have a sharpness at the interface. And try to measure the film thickness. That's one of the way. But during the growth, we usually try to look at the read signal. But the SrRuO has a step flow mode. So after 1.5 or 2 unit cell growth, it's difficult to see over here. So by measuring this time, we stop over here and assume that this is a 4 unit cell. But only good evidence is this STM images. And as you say here, some of the, if you look at the thickness over here are a little different. So there's always an inhomogeneity. Okay. Mm-hmm. From the bottom layer. Okay. So in here we have the house photon emission setup. The escape depth is usually less than 10 angstrom or 5 angstrom, typically they say. So it's usually all the signal is coming from the SrRuO from the 1 or 2 layer from the top. Yes? Yeah. We are using the lab setup. So we are using helium, they call helium 1, helium 2 kind of setup. And that is usually give the escape depths about 5 to 6 angstrom or so. But if you go to the synchrotron radiation source, then you can actually the electron escape depths will become larger. So you can look at the bigger. You can with a small angle, but still we can actually change the polarization. So from that we can determine what kind of orbital contributions and so on. But it's not exactly normal with a certain angle. Since it's not my my expertise, I do not know the exact number, but it's about 30 degrees or something like that. But I do not know the exact number. If you want, we can check for you later on. Oops, it's not, for some reason my cursor didn't work on the screen. Let me move on. I think I have to give up my simulation because for some reason my cursor in here does not move at all. Sorry. It's frozen for some reason, but I hope that I can survive. Okay. Okay. Okay, now it's better.
Now it works?
I think now it disappeared.
Is there a short key to unlock the pointing?
I don't know.
What you can do is just move the angle of the pendants and then
Let me see.
No? Yeah, so when you does this not work?
Okay, let's try this.
And if
Oh, okay. Okay, good. Thank you very much. Sorry for the technical difficulties. So now, what we want to do is try to induce a meta-initial transition by controlling the tilting angle, oxygen octahedral rotation angle. I think because in 214 compound, that is already well known. So we want to see, can we realize the same thing in the one unit cell, 1 and 3 thin film? So this is the electron structure diagram you already saw. So this is what we expect. So we grow the 4 unit cell SrRuO and go to the synchronous radiation source and 80 electron volt. It has a big penetration depth, escapation depth. So even though film is not high quality, we still can measure it. And this is the electron structure. The band structure around the endpoint over here looks very similar, and the line is the predictions from the theory. So this is a really good the electron structure. But this is I already explained to you. So there are big effects coming from rotation of the oxygen octahedra. So we think about 2 systems. So let's suppose grow SrRuO on calcium titanate. So in reality, it's a buffer layer. But anyway, calcium titanate is a large octahedral rotation, and in gradual rotation, it has A minus, B plus, A minus. A. Well, on the other hand, STO is nearly cubic. It has tetragonal, so A0, B0, A0. So it has a little OR rotation, but that will have a larger OR rotation. So by doing that, we can control the bandwidth. So if you go from this direction to that direction, bandwidth will decrease. So we should have meta-initial transition by mode. So originally it looks like this, but as the T decrease, then you will finally enter the insulating state. So can you observe this kind of phenomenon? So we developed a SrRuO system. So STO, then we grow the BTO on top of it, then single layer of SrRuO. STO, single layer of SrRuO. STO substrate, calcium titanate, single layer of SrRuO. So if you move from this direction to this direction, oxygen octahedral rotation will become larger and larger. See? And this is a TEM which show we have a very good samples and so on. And this is a read pattern, and there's a surface reconstruction occurs that agrees that from our distortion, this angle will become better, and the structure changes actually occurs as we expected, and so on and so on. So this is the geometries we used in here. This is the angle averaged the photon emission spectroscopy on STO film, STO substrate, like this. Even for the one unit cell sample, you have a very good finite tensile state. So that's metallic. But here, it becomes insulator. So metal insulator transition occurs in the one unit cell SrRuO thin film by controlling the OOR rotation. So this is the Fermi surface map. So, so one unit cell, I think, with a abstract substrate, 4 unit cells are clear Fermi surfaces. Even for the 1 unit cell, you have some. You can see some status over there. But when you put the calcium titanate in middle, no Fermi surface. So it becomes insulator. So we can induce metal insulator transition. And also, this is on barium titanate, strontium titanate, calcium titanate. So we increase from here to here, so increasing the OOR rotations. This is a 4 unit cell sample, 3 unit cell, 2 unit cell, 1 unit cell. Last time I showed you this one. This is all metallic, but this becomes very blurry, so it's quite incoherent. But if you move to the barium titanate, even for the 1 unit cell, you have a coherent metal. It's a very clear Fermi surface. But in here, it all disappears at the insulator. So metal insulator transition can occur in the middle. And also, this is a density of state. You can see that with the barium, you have a high density of state. Calcium insulator, this is a barely metallic. So now our question is that, does it relate to the orbital degeneracy or Hund's metal state? That's one of the important issues in transition metal oxide, but not many people address this issue, particularly with experiment. In theory, there's a lot of interesting predictions, but experimentally there's quite a few. So we have to go back to the Hund's rule. So in quantum mechanics, if we have a multi-orbital system, we know that we should maximize the total spin first. Then we try to maximize the total angular momentum, and there is another small third rule there. So let's think about the T2G electron system we are dealing with. So there's 3 orbitals, 3 T2G orbitals. So let's assume there's 2 electrons. Why not 4 electrons? There's an electron hole symmetry. So 4 electrons in 3 orbital system have the same physics as 2 holes in the 3 orbital system. So it's basically the same thing. So if you do not follow any rule, then let's assume that there's 2 electrons the same level and the opposite spin, because the Pauli exclusion principle do not allow the same spin at the same orbital, then S equals 0, L equals 0. The Ornstein correlation U is here. But if you just follow the second rule, then you have S equals 0, L equals 1, like this. But if you try to satisfy those 2 rules, you have to make a total spin large. So you have to put these 2 here, so S equals 1. The total angular momentum is 0, is 1. Here's the L equals 1. But in this case, if you do the calculation properly, you will find out the energy state is the U minus 3J. That's all done by the George et al. From the Paris. So this has the lost energy. That's what the Hun's rule said. So for the multi-orbital system, just like a strontium-leuconate, this kind of the exchange interaction should play a very important role, and that's the reason some of the metal has a very incoherent state, could have an incoherent state due to this kind of correlation coming from. That is a Hun's metal, but there's, as far as I know, there's no experimental evidences for that. And another interesting theoretical prediction is that if we have a 2 orbitals of a 2 electron, half-filled system, 3 orbitals and 3 electrons is a half-filled system. For the half-filled system, the Martin-Schleyer transition occurs like this. As J increase, this UC decrease. But for the other film, it actually increases. So it behaves differently. So that's one of the important point of this multi-orbital physics. So this is a very nice phase diagram that's proposed by them. So this is a 2Tg electron system. For the half-filling system, okay, this area is the metallic system. This is the insulator. As you increase the J, this UC going down and down. If this direction of the arrow indicate that. But for the other filling, actually it's coming over. So even you have the same kind of the T2G system, depending on the filling factor, the role of the J will play a different role. So, and also near the metal-initial transition over here, the quasi-particle weight will change, and it will actually indicate the Hun's metallic cases and so on. But in our case, we are looking at this one, this area. For strontium leuconate, calcium leuconate, and those 1 and 3, with a large U value with a Martin-Schleyer, small U as a ferromagnetic liquid, in middle, you should have a Hun's metallicity. But unfortunately, if you look at the calcium leuconate, strontium leuconate, and barium leuconate, you grow the very thick films like this. This looks like a bulk, and the alphas, they are all located over here. So it is all ferromagnetic state. It never go to Hun's metallic state. But by controlling this factor, we make this ferromagnetic, you will enter this region. This is the region we believe that this state become highly incoherent and so on. But unfortunately, we couldn't measure all the quasi-particle, the density and so on at this moment, because our data is not still good enough to do all those things. So this is all indirect evidences. Yes.
Signature of the Hun's metallic state will be this highly incoherent.
Yes. So Hun's metal is the system near the metal-initial transition, but the correlation is driven by J, not U. That's the Hun's metal. So it's quite complicated how much incoherence is coming from U or how much coming from J. So we have to do a lot of the detailed experiments, measure the electron structure exactly, and we have to compare with the theory very carefully and so on. But at this point, we do not have that kind of really high quality data anymore at all. Okay, so but still, this is open for everybody. So this is DFT, but anyway, so if you do the DMFT, you can see that in this state you can have a metal-initial transitions and so on. And here's the state, and if you do the calculation, there's a quasi-particle peak comes out and so on, but we still do not have a exact experimental data to compare with. That's the current status. But still, we believe that, we start to believe that this should be a Hun's metal. So questions up to here? If not, maybe I will move to the next one. So now, since we have this, So what we try to do is that we have a metal oxide octahedra. Instead of rotating this metal oxide octahedra, what will be happen if you try to extend or squeeze like this? This is typical you call as the strain engineering. So let's do the strain engineering to this system without tilting, without rotation. So the simple schematic looks like this. So we start from here, near the Fermi surface, XY and YG orbitals are mixed together. But if you increase the crystal fielding, crystal spreading, field spreading, then the band will start to move. Particularly the XY will move down. But at a certain point, XY will move down up to this point. So if you fill it up from the bottom, the old XY level will be completely filled. Then you have in the YG and GX axis, it is only half filled. Then what will be happen is that since it's a half filled system, you will have U start to play a very important role. So it's a Mott insulator. So if you move from this direction to this direction, the band will start to move like this. Then at a certain point, you have a Mott transition. So can you observe that? And also, this is exactly one of the reasons that electron structure in 214 calcium strontium leucine compound are changing. But not many people actually address that point. But we believe that is exactly what is happening. And another important thing is that in here, we have 3 orbitals near the Fermi surface, and there's a 4 electron. But in here, near the Fermi surfaces, this is completely filled, so this is actually out of our concern. So we have 2 orbitals and 2 electrons. So we are actually controlling number of orbitals as well as number of electrons in this system. It's a very unique way we can control. And for 4D transition metal oxide, this kind of thing should play a very important role if you want to do the oxide electronics. So what we try to do is that we try to grow some SrRuO thin film using different substrate, which has a different lattice constant. But unfortunately, they have all different rotations of the rotation. So if you look at the structure in the Grazer rotation, some of them are this one and this ones are different. So if you grow the thin film on top of it without this STO layer, the actual structure in here are different. Depending on the substrate, they will have a different tilting angle. So in order to overcome that one, so we grow the 10 units of the STO in the middle. So this, the inserted layer will guarantee that this will have a nearly same symmetry. Yes?
Is it obvious that STO would maintain the same rotation pattern across this pretty wide compressive tensor 3?
Oh, this one. Yeah. Very good question, but we have to confirm experimentally. That's our role. So in order to publish our data, okay, we have to prove that it's true. So we all try to grow. This layer will have this A0, A0, C minus. So what we first did is that we read the lead pattern. We look at the reconstruction, but see that there is no change in reconstruction on different kind of substrate. So the symmetry is pretty much the same. And also we look at under the TEM. Of course, there's the limitation in TEM observation, but still within our observation, they look pretty much the same. So we call that this is a symmetry preserving buffer layer. So by using this technique, we can grow the 5 films with a different lattice constant, but the OR rotation are pretty much similar. So that's the strain engineering we try to push. So from there, what we want to do is that by elongate or squeezing our data, we want to make some changes. But if you make a elongation like this, originally the three-fold degenerated T2G level will be split into two. There's another crystal field spring. So XY level will be lower and YG and GX will be higher. So if we try to fill the 4 electron zone in here, then this will be completely filled, and this become half fill. So this is the, the schematic diagram in terms of the band picture. Originally it looks like this, but if you enlarge the crystal field splitting in here, then XY become completely filled, so it become an insulator, band insulator. But the last, you will have a band, but it's some kind of a near the Fermi surfaces. The U start to play a very important role, so it's a still incoherent band like this. But if you increase further, then you will enter into the insulating state, mud insulating state. So the gap is opening, two kinds of gap opening. One is the band insulator gap opening, as well as a mud gap opening. So there should be a simultaneous occurrence of the gap opening and the insulator gap opening, as well as the mud gap. And also in here is effectively 2 electron system, 2 orbitals, and so on. So I try to skip because this is the way we can identify the orbital occupancy and so on by using optical spectroscopy. And I happen to be an optical spectroscopist a long time ago. So we measure the optical spectroscopy. We find out that in this limit, if you look at it, this is a fully filled, this is a half filled. So really, okay, sorry. Oh, I don't have a time to enter to the topological aspect. But anyway, so this is the highlight of this part. So you can see that this XY orbitals are slowly moving like this. But this XG and YG orbitals, there's no gap. So Fermi surfaces are still located like this. But suddenly, there's nothing in here at the Fermi surface. You have a very bright state at the UV. So this is a mud gap develops around here. And the reason why suddenly you have a mud transition here is actually related to this multi-orbital physics. When it become originally, we started from here. Over here, if the J increase or something happen, then it actually, the UC, the critical sequence go, meta-initial transition go to a higher parameter space. But if you have a half-field system, it will go down. So by controlling into the half-field system, we can make this mud transition emerge very clearly. This one I want to skip. And the final point I want to make about if I have a time, maybe I will just talk about a little bit about topological aspect. Sorry. Okay, so SrRuO is known to have an anomalous Hall effect, and a very good introduction is already given by Professor Cabegrier, so I don't have to go into detail. But this whole data is proportional to the magnetization in this region. And year 2002 or 2003, Nagao's group already proposed that if you look at everything in the momentum space, it looks like this, and they call this a magnetic monopole. So that's the beginning of the actually topological effects studies in this field. However, there's not many studies to observe this one. It is reported actually for other 2D material system. I just didn't. But even for the strontium leucine, they never measure the electron structure. Yeah. But more generally, nowadays, people believe that if you have a magnetism and spin-orbit coupling, so if you have an itinerant ferromagnet, you can have a topological effect. Two important conditions is that if you have a spin polarized band with a nodal point, and if this nodal point or nodal line become lifted by spin-orbit coupling, then you can have large the Berry curvatures, and it can lead to a very large anomalous Hall effect. This is a current understanding. This is this morning well explained by previous speaker. But anyway, so in my university, one of my colleagues mentioned that we are working on the perovskite structure. So if you have this perovskite structure in 2D limit, and if you have a spin polarization, if you turn on the spin of coupling, then it will automatically generate the largest. It doesn't have to be strontium leucine. It's a very general behavior, he said. So what we did is we did the spin alphas and so on. So below TC, you have a splitting at the near endpoint, but above T, no point. But endpoint is really important because our calculation saw that near the endpoint, with a spin-orbit coupling and magnetization, you have a quadratic band crossing circles over here, and they claim that this will play a very important role in topological effect and anomalous Hall effect. And this is the theoretical prediction that this is a point that Berry curvatures have become very strong near the endpoint because the band crossing was lifted by spin-orbit coupling and so on. And experimentally, with a crude method, the circular dichroic alphas, we can get some signature. But still, we do not have enough high experimental resolution to prove that this is actually completely satisfied. So we are still working on the problem. So this is a summary. So in the ultra-thin limit, we think that we can control the dimensionality, strain, and proximity effects. So we can actually find out lots of the new emergent phenomena in here. Finally, actually, I retired from my university position last year. I'm still working on the director of the center. But my position will be finished at the end of this year. So my group looks like this for about 3 years ago. Well, now I have only one student. So most of the work has been done by former students. They already have relatively good postdoc positions or the industrial positions. So this is the Jung-Rae Kim, who is Caltech, and Eun-Gyo Ko, who is at Stanford, did a great job in growing the high-quality film and the RPS measurement. And Byung-Min Son, he did a great job in all these data, and actually recently got a job at Seongyungan University under the guidance of the Chang-Hyun Kim. STEM is actually this worked by the Jun-Sik Moon under the supervision of the Mi-Young Kim. And we have a really excellent theoretical collaboration led by the Bom Jung-yang and Chung-Young Kim. So without their help, none of this work is possible. I did almost nothing, but they did all the work. But anyway, so thank you very much.